All right, our next speaker is Phil Nigh, and he will talk about a topic that has come up in the previous questions. Phil is a distinguished technical staff member at Broadcom's ASIC product division. He's responsible for driving quality and test improvements for 7 nanometers, 5 nanometers, and 3 nanometer products. He's worked in IC testing for 38 years, including for Global and IBM, and has over 25 patents. He has also organized the Industry Test Challenges workshop for over 20 years and is on the program committee for a number of conferences and industry groups. Phil has a PhD from Carnegie Mellon University, and today he's going to talk to us about test challenges and directions as the industry moves to 3D heterogeneous products. With that, I'll turn it over to you, Phil.
Okay, thanks, Ravi. So during this talk, I'm going to talk about a lot of the challenges related to moving to heterogeneous integration and chiplets. I'll talk about some, call it potential solutions, but some of these things don't have solutions. So I'll say some of the challenges also as that we need to get there. And also, it's important that I'm coming at this from my point of view. I work in the Broadcom ASICs products division. We mainly work on leading edge, advanced technology stuff, AI, data center chips, networking, computing. So I don't have experience, and so that's going to be my view coming from that area, performance oriented, rather than maybe commodities and low cost. And I added a pointer here to the heterogeneous integration test roadmap, and I think that's an excellent reference. A lot of good material on most of the things I'm going to be talking about. And just a little bit more about Broadcom, what we're doing for ASICs. Here's an example of a 5 nanometer ASIC. This was announced last November. I'm not sure how many chips and chiplets. Maybe, I know there's some HBM2Es on here. There's at least 3 or 4 other chiplets, but this is kind of the general market that I work in. And from ASICs, typically we partner with system companies and we develop the solution for providing this. So as far as an outline, I'll talk about what is the general challenge, where I think we are today for multi-chip products, talk about both 2.5D and then 3D. And a key thing related to test is the bare die market, how we get chips, how we integrate them on the package, and then how we test them. So I'll talk about the test challenges along with industry standards and where we are. And there's a few good industry standards there, but they don't solve everything. And then some of the best practices moving ahead. And then a topic that's very challenging, and that is how we could enable end-to-end data analytics to optimize, find root cause on problems, etc. So really the first project I had was working on I think it was 90 chips at that time. Within a year or two, went to 121 chips, a multi-chip module. And we build these, we test them at wafer probe, we build them, we test them in the system. And then if a die failed, they would either send me the whole MCM, but typically they pull the die off and send me the die and say, we think this die has a problem. And definitely and then I was expected to come up with a new test that would find it. Both that was a cool project, and I learned a lot, both about multi-chip in general and test methods. So here's some charts from Dave Armstrong, and this was part of the European Test Symposium. I think the panel question then was this path to productivity. Where are we with 2.5 and 3D? And I like the way Dave answered it, because there's not one answer. It depends really what technology you're talking about. For example, if you're just talking about, let's say, HBMs and providing HBMs, I'd say that's relatively mature today. If you're talking about 2.5D with a silicon interposer and HBMs, I would also say that's mature. Having said that, both of those, in general, the cost has to come down for these technologies to have broad use, especially in the commodity market. If you're talking about stacking chips, and Intel's shown micro bump stacks. Not sure if that was high power or not. I don't think so, but I would say it's still in development. Thermal management's a big deal, particularly with copper hybrid bonding. And especially if you're putting chips together, more than 2 chips in a stack, and thermal management, again, is a big deal. And to me, really, the big challenge looking ahead is, let's say you have hundreds of these bare die and you want to pull them together in a package. You get those from many different suppliers, and somehow you have to make all of it work. And I would say this is in the planning phase. And when I think about it, here's kind of an example of the type of problem looking ahead is imagine call it a package with 4 processors, high power. And then on those, we use copper hybrid bonding, and we put, let's say, 8 SRAMs per processor. And we connect the processors with some kind of local interconnect. A lot of the same challenges and methods would work with bigger interposer, but let's just call them local interconnect. And then you have to talk off the package, and I just put SerDes here for an example. Actually, it probably have many more SerDes chiplets for a product like this, but keep it simple, let's show 4. And then we have HBMs also connected. So if you just look at this and count each HBM slice as a different bare die, this has 122 bare die. And this brings out a lot of the challenges I think we're seeing in general from the industry and from a test point of view. So I think about this as this is really the challenge moving ahead. One question is, where's the industry going, let's say, over the next 5 or 10 years? Will it be 8, 10 years from now where there'll be a catalog and you can just look up the chiplet, you can order it, and you can know when you get it, you can just plug and play different chiplets and it'll work? Or will it still be kind of basically an evolution of what it is today, that if you're a system integrator pulling this together, let's say in testing and shipping them, well, you mainly work with a small number of trusted partners who deliver you silicon, and you kind of stay within that club. And you'd only go outside of that club if you needed a new function, for example. And I think it'll be more like the second one, probably for 8 to 10 years. And that is, there won't be a catalog where you can just, on the right, imagine buying to put on one package. I think there's 8 different examples of chips here, and we're going to buy these out of the catalog. We expect them to work. Everyone knows what has to be delivered, how to test them, and that we can just buy all this stuff, put them together, and it's going to work. I think that's probably for more than 10 years. And we want to keep thermal in mind also, that's a big deal. I won't mention that a lot in the rest of the talk, but it's fundamental to both testing and building these parts. Okay, so just to make sure it's clear what I'm thinking about when I say testing, imagine you're getting these chiplets shown on the left. The supplier is going to do some kind of wafer test, might be multiple insertions, but just to keep it simple. And then there has to be an integrator who pulls all this together, owns final package test, delivers the product, and is responsible for quality, yield, reliability, et cetera. And probably the customer that receives this part doesn't care about who's supplying all the chiplets. In other words, the integrator has to take care of all that, including any chiplet related quality or yield issues that the final customer may see. And so it's a big question I'll keep coming back to, but for example, what testing do you need at the final package test? Do you need to reapply some or all of the wafer level tests? Can you even do that? What I've heard some products is that even the packaging process itself will change the characteristics, and therefore they have to be retested at the final package level for performance. Well, things like calibration, personalization, harvesting, all of that, some of that will be needed for specific chiplets. All of it would be needed if you show all the chiplets like I show on the left, along with things like RAM repair and lane repair would be needed at the final package test. So the challenge is, how do we do all this stuff? And what some companies are doing, and they're really starting this with single chip packages, but I think these multi-chip packages will accelerate it, is to say, okay, I'm going to need an additional test step where I hit this package part with a bunch of functional tests that maybe weren't done at earlier AT structural tests, just to bring the quality levels up to the what's required. And the key thing of this SLT stands for system level test, but it's really running functional test in a socket. So the parts aren't soldered down on that part at this point. Their SLT would be used for screening. Okay, one point is the main concern really isn't testing, it's yield. In other words, let's say we could throw all these chiplets together. We could test it very well at that point. But the problem is that if you don't test it well at the wafer probe and you don't have a good test plan, yield could stink at final package. So, and I just put some numbers there. The numbers are obvious. They multiply a lot. If you're doing, tens or even over 100 bare die, that pretty quickly, if quality for those dies aren't great, the fallout's going to be significant. And numbers like fallout of 20 to 40% are just unacceptable. And so in general, people would love to drive as much testing back to wafer probe as possible, all of it. Question is, okay, is that possible? There's some other challenges related to that coming up. And again, I'm going to have some other examples, but how much of this needs to be repeated? Ideally, you wouldn't have to repeat tests at final tests that were done at wafer probe. So known good die. Jan mentioned it before, although she said people have been talking about for 30 years. However, I still can't get a definition on what known good die really means. I know, and people have come up with other terms like known shippable or something. I think what's required is not, but for one thing, everybody ought to know that known good die does not mean all the chip bare die are good and will pass. Anybody who thinks that would be wrong. They're not all going to work at package test, or at least work initially. And that's why instead of trying to think about a term like known good die, what I would like to hear is just tell me what the guarantee is for the number of parts that would fail at the next level of assembly, and both time zero and then reliability. And bare die suppliers should be able to supply that. Having said that, I've seen examples where getting a number like that is challenging from suppliers. Also, bare die suppliers should provide test information. If I want to redo tests at the package test, I need to know how to do that from the bare die suppliers. And that's another area where I think today the industry is basically very immature. And I'll make some other points related to that. And the Mark Twain quote has something to do with what was his quote? There are lies, damn lies, and I was going to say known good die. But key point here is don't assume known good die means all the bare die are going to pass. And that gets it. So really the fundamental question is how to achieve low DPM or good quality for the end customer. A major challenge in this is how you do wafer probe testing, particularly can you probe all the signal IOs, for example? Obviously, you need to do power and ground. And it's today, I would say, for at least things that I've been involved with, it's really expensive if you even try to do it. And even if you try to do it this generation, the following generation, you can't do it. So the only approach is some kind of reduced pin count testing at wafer probe that still provides very high quality when you put those parts in the final package. And especially when you think about copper hybrid bonding. Instead of maybe today, the number of signal IOs, maybe 500, 1,000 for some of these ASICs. Next generation, that'll multiply at least by 10, maybe 20, 30 more signal IOs. So there's both no ways you can test it. And then the question is, okay, how do you deliver quality? One point is that at board level, there's this 1149 JTAG boundary scan. I don't think you'll be able to use that when the number of signal IOs explode. You'll have to come up with other methods, lighter methods, which still allows you to test without touching all those signal IOs at wafer probe and getting good quality. And I think the way to think about it is instead of thinking about this package part as a board of different components, you have to think about it like it's a big SoC and more like, chip to chip connections or more like big vias on an existing SoC rather than a board. And kind of the rule of thumb I have, if the packaging people know how to build it, designers will use it, and it will be built. And we're going to have to figure out how to test it along the way. And Ravi, let me just pause for a second for questions. If not, I'll keep going.
No, actually, Phil, thank you for pausing. There were two questions. I didn't want to interrupt you, but let me ask. Uh, One question is on chiplets in different nodes. Are there different tolerances on Z height that affect heat sinking methods? This is a speculative question. I'm not sure it's for you per se, but I'm sure you have an opinion on this.
Well, only that the answers, I've seen that, and I've seen equipment providers. I'm not an expert, but I've seen equipment providers say, yes, I can handle that. And I don't want to say for any kind of multi-chip package, but let's say a simple 2.5D ASIC plus HBMs. I think there are industry equipment solutions out there, but I'm not the right one to talk about those in detail.
I'm sure we will revert back to this. The other one was this. You may have an opinion. Beyond supply chain, how will the packaging supply chain look like in your mind?
Well, that goes back to the point about how will the industry evolve. And at least for the Broadcom ASICs I work on, it's not as complex as what we're talking about here, where you may have to deal with 10 suppliers of chiplets coming in and figuring that out. There's basically mainly comes from one foundry plus HBM. Broadcom also designs a lot of its chiplets. So it's a relatively smaller supply chain than maybe somebody who has to buy chiplets from 5 different companies. And that would be more challenging.
Nice. I'll take one more question and then I'll let you go on and we'll come back to the questions. How do you perform pre-bond test? Where do you probe the microbumps or the dedicated pre-bond pads? I am assuming this is a question related to hybrid bonding, but I suspect more than that.
Yeah, and I think what I've heard, both within the company and from people in the industry, there's this term no touch. Okay. And no touch, I think, means that you don't touch them. So in that way, the only way to do the testing is both power and signal IO is through sacrificial test pads, maybe some kind of aluminum pad, but that's area overhead also. So that's where you're not going to have a lot of test IO, for example.
Yeah. Phil, there's other good questions, but I'll let you move forward.
Okay, thanks. Okay, so what are you going to do at final test? You're going to do repair. Some parts need calibration or personalization. I included the term some people in the industry are calling harvesting. And I know the AMD folks have said that more or less means once you get to package test, you don't want to lose any die. It's too expensive. You lose everything else at that point. So instead, you want to personalize the die enough so it's still functional. And again, I've heard some products may change during the packaging process. So you have to somehow do some testing at final test, I think for all silicon, some level. And the bottom point is that the package integrator, I believe, should plan to have the option to apply as much of the wafer probe test as possible. Ideally, all of it, that you can reapply at final test. Whether you actually have to turn that on or not will depend upon other details, but I think it should be planned in. Let me give you an example, the second red bullet. Let's say you're running and all of a sudden there's a quality problem with one of the chiplets. You go to the chiplet provider and you show them the problem, they fix it, and they start testing. And then all of a sudden you say, by the way, there's about 30,000 parts already post-wafer probe test headed for final test. What are we going to do with those? That's where this option of being able to apply more wafer probe tests at final test is important. Also, in some of our customers, let's say there's a problem with the final package part. We can't share that final package part with all our suppliers. We can't pass it around and say, redo your tests and see if you find the problem. Maybe some companies can do that, but that's one of the restrictions. So as system integrators, the buck stops with us. So then the question is, well, imagine you're building this package part, you have 10 different chiplet suppliers. Are each of those going to supply all the test information you need to redo the required tests? Is it going to be built into the design? Will they share it? Or will they view it as, say, no, that's our proprietary secret sauce, and I don't want to share that with you? Now the question is, will industry standard solve the problems? It helps in some areas. The HBM spec JESD 235 is excellent, has been out like 8 years. Having said it, may not be sufficient for all products if you just follow the JESD 235 recipe, but it's an excellent industry standard. Somebody asked about 1838. Nice standard, getting momentum, aimed at 3D chips. Excellent start, mainly aimed at digital. If you think about 2.5D chip-to-chip interconnect, I know within Broadcom, we've done a number of these, and most of what we've done, we've designed within Broadcom. Tomorrow, Bapi Binakata is doing a talk on ODSA. Sorry, typo. I'll fix that. But there's industry standards trying to work on this chip-to-chip interconnect. I know from Broadcom point of view, we're all about performance. And so standard be nice, but if we have to give up performance to follow it, we might not. And for things like, we're definitely headed toward some of the 5G multi-chip applications that need high speed B to A's and A to D's, which need to be calibrated at the final test step. RF, silicon photonics, I would say for most of those, there's no industry standards as of today. And for some of them like RF and even the high speed A to D's and D to A's, the designers say that's no touch also as far as DFT. They don't want us putting in DFT around that, giving us direct access. So just briefly, JESD 235 is nice, addresses a lot of the test issues. It's built into both the PHY on the processor side and then the HBM. But it may not be, if you just follow what's described in JESD 235, it may not be sufficient. And then here's just 1838, nice access to each die. It's nice. When we've looked at it, we liked it because it doesn't add too much area overhead if you want to do something like just add relatively light wrappers around each die and maybe around IP. So at first look, I know Broadcom, we like it. As we look in the future, whether it applies for 2.5D is a question, just 3D, some of the details we're still looking at. Okay, final topic, end-to-end data analytics. And this will be challenging. So there's over the last 20 years, there's probably been 40 PhDs who got their work in the statistical area and kind of test and quality area. A lot of good work there. Just briefly, if you get bare die, don't assume all bare die is equivalent. Here's a very simple old example where all the black die are bad, or excuse me, black die are good. They're passing dies. Red dies are bad, and green dies are good. I just want to use the green dies as an example of goods. If you notice, this is relatively poor yield, but yield. And if you look at this, the die on the right, statistically, it has much higher quality than the 3 dies on the left. I say 20x, actually could go up to 40x in some data we've seen. So there's big differences in this incoming bare die about the quality levels. Also, here's a set of chips, and I just called it Beamin and speed, but a bunch of chips, these all pass to the spec. So that these chips are all passes. There's some normal chips, and then there's some outliers. This is again a case where these outliers could be 10x, 20x worse than the normal die. Now the question is, and everybody's known these statistics for more than 20 years. The question is, okay, how do we use that to our advantage? Also, what I don't show and probably should have is there's like wafer to wafer yield variability, which affects quality also, and lot to lot and tool to tool and time period variability. So you have all this data. And then the question is, why is it important to be able to use this data? Let's say final test yield drops and that who's ever using it says, okay, I'm finding more fails at the system level, and I only find this with functional test, and I don't know what chiplet has the problem. Ideally, what you'd like to do is be able to say, okay, there has to be a problem. We can probably see the problem if we looked at all the wafer probe data, but if I'm getting chiplets from 10 different suppliers, am I getting all that data? Am I getting any of the data? Do I have to go to each one? which I don't want to do. That would be very inefficient to go to each chiplet supplier and say, start checking this. Do I have the traceability, the per die traceability on the fails versus the passes? And
Phil, do you mind if I interrupt? Because there's an
sure.
excellent question associated with this, which I think you can answer quickly. Just as you said, when system level test fails, we like to correlate the fail with structural tests done at IP, right? So for chiplets that come from different vendors, would that even be feasible in your mind, or should we take a different approach to debugging?
Oh, well, no, that'd be nice. But a lot of times SLT uses functional tests that's notoriously hard to debug. And so that's the first step is, can you get it to the chiplet, or could it be any place on the chip? What kind of diagnostics can you do? So driving SLT fails back to ATE, call it, wafer probe, no matter if it's chiplet or not, is challenging. And I think it'd be even more challenging in the chiplet environment.
Yeah, fair. Thank you.
Okay, so just to finish, I mean, the vision here is to collect all this end-to-end data. And when you have any issue, you can quickly go have software tools that can go through this data and says, here's the correlation. Okay, here's the chiplet that's the problem, looking at that data. But will you have that? Will anybody have that data? All of it together in one place. And again, what you don't want to do is go through the fire drill of, okay, we have a problem now, let's start pulling all that data together. That's almost impractical. And here's a chart that shows this. This is from the HIR adaptive test roadmap. The link's there, but it basically says, okay, try to pull all this end-to-end data, including SLT, system, and field data in a common place to enable these analytics. Okay, so to finish, yeah, I've really already talked about these issues, but a few of the major challenges are wafer probe testing, making that as thorough as possible, even though you can't probe all the signal IOs. What should be done at final test? And how do you support test at final test, working with multiple chiplet suppliers? And then this end-to-end data analytics, which is, if you really want to do it thoroughly, like I just talked about, I would say is challenging, and some people would say not practical. Thanks.
Phil, I'll see if we can do a rapid round of questions to get through. There's some really good ones. The first question is, how do you think photonics interfaces will change chiplet testing?
Oh, that's a good one. I have a little experience with photonics, but not a lot recently. And do I have anything useful to add? Not besides the obvious photonics test challenges, like how do you do alignment is the big one. Typically, electrically, that's the easier part rather than alignment. So to be honest, I don't have a lot of useful stuff to add there, except this is coming.
Nice. The next is a question that I'd love for you to speculate on. I suspect it's a broader question, but how do you see the world of 3D stacking evolving? Other than HBM to logic or logic type devices, also the cost of these processes, how do you think those evolve?
So one point is, if you say a 2-chip stack is 3D, okay, that's there. As Intel's already announced stuff, AMD did with the SRAM chiplets, Broadcom's working on stuff that to me is fundamentally different than 3 or more stacks. 3 or more, it's all about power management, thermal management. And so that I don't know. I even with 2-chip stack, it's challenging, but I think there's options. But the first question, it's all about thermal to start.
And Eric has a couple of excellent points in addition to a couple of very good questions. Let me see if I can synthesize them. If you assume that in post-bond testing you are able to test all dies, you might not always have physical access to probe interfaces for those various chiplet dies. So how do you see DFT being built into this? And is there a way of doing modular structural tests to offer you a first-order diagnosis on test-related issues?
So ideally, yes. A lot of the digital interfaces, there's options. But again, I'll use high speed A to D and D to A. And I know when in the past, and we had chatted with companies who produce those, and we said, we want to add direct access to those chip to chip interfaces. They said, no, you don't get it.
Yeah.
And so adding DFT and that's why RF is a big deal, high speed analog, those are challenging. And I think it's going to be things like, okay, you don't get it. You got to figure out both testing, Loopback methods are nice for some of that, but both loopback methods and you're going to have both good enough yields, high enough quality coming in from wafer probe testing, so that given if you don't have access, you can still, produce parts with good enough yield.
Yeah. By the way, excellent thinking on the data analytics. I'm always impressed by how much information we miss when we don't do this cohesively. So thank you, Phil. This is excellent.
So once again, thank our sponsors, Advantest, Omcor, and Synopsys, who made this event possible. Advantest rated the best ATE company 2021 in the VLSI Customer Satisfaction Survey of 2021. Omcor, as we heard an excellent overview from Dave as to their work, but as the leading OSAT with differentiators in the area of technology, quality, and service. Synopsys, with their vision for supplying solutions from silicon to software. And with that, I will thank everybody for joining us today. And once again, thank you for your attention and your participation. And we look forward to seeing you again tomorrow at 8 a.m. Pacific. Thank you.